Today I wanted to talk about designing sprinkler systems and their effect on means of egress. And I wanted to do something interesting, and that is show in a performance-based analysis in terms of how to calculate when a sprinkler head initiates. And there's a lot of reasons why an engineer would need to know this. Most people that are watching this channel probably more are into the codes than the science behind the codes. So this little video, it's actually to show you what's behind the scenes so you can understand it. If you look at the IBC or the IFC, specifically Chapter 10, the means of egress section really coordinates travel distances, dead end lengths, corridor sizes, that kind of thing, to support what comes out to be 3-minute egress. You're not going to typically go above 3 minutes. So that's really the target of what you're designing for. And it's buoyed up by software and engineering approaches for that. Sometimes you need to know when a sprinkler head's going to initiate. And I want to show you how to calculate right now. Let me show you some stuff. So when you're calculating the basic times for egress, you're going to follow this model. It's called the hydraulic model. This is from the Society of Fire Protection Engineering Handbook of Fire Protection Engineering. And I'm not going to go through this whole chapter. This chapter is kind of lengthy, but it basically has little formulas that feed into this formula that help you calculate overall time to egress. And a piece of that is detection, but another piece that needs to be considered sometimes is the performance of the environment. So typically smoke layer level is capped at 6 feet. So if you're below that level, you've basically made that egress access path problematic. You're going to be slowed down for that. So here's some equations that help you gauge some smoke plume temperatures and velocities associated with a fire. So these are called the Alpert's equations. They're as well in the SFP handbook. And I want to show you, this piece is really not in the handbook, but I want to show you how to calculate it. So if I had a typical fire, like a trash can fire, for instance, you can actually go and find data that models how much energy is released from a trash can. Generally speaking, it's going to be about 100 kilowatts, and there's some variability there, but I want to show you a source for that information. NIST is the National Institute of Standards and Technology, and they have a fire calorimetry database. So they've actually gone through and used oxygen calorimetry to be able to estimate how hot fires are and how long they last. And they use the relationship that there's about 13 megajoules, 13.1 megajoules per gram of oxygen, I think is what the correlation is. And it's pretty much across the board. It's really a steady state value. But if you just measure your oxygen output from a fire and know what the input oxygen concentrations are, then you can calculate overall heat release. And that's how that system works. But if you look at it, here's an example of a trash can from that database. And I'll go ahead and run this profile. I went ahead and press the press the button here. This is a 30-minute fire, and it's been basically condensed in very rapid mode in just 16 seconds, just to show you the behavior of this fire. The peak of this trash bag, it's actually a trash bag, is 115 kilowatts. Putting that into perspective, if you've used a hairdryer is about a kilowatt, thereabouts. Maybe a little bit more, maybe 1.5 kilowatts, depending on what you're using. So even at the top rate, 1.5 kilowatts, you're going to be about 60 or so, maybe 75, 80 hair dryers all burning simultaneously or on simultaneously to produce that 115 kilowatts of energy that this fire produced. That's how you can gauge how hot a fire is. But the question is, if you're in a suppressed building and you had a trash can fire, well, how long would it take for that fire to initiate a sprinkler head? And I want to show you a couple differences in terms of sprinkler heads. If you go to NFPA 13, that's the standard for water-based fire suppression systems. And there's a value, there's several values associated or characters of sprinkler heads you should consider. One is called the RTI. That represents the response time index. And the lower the RTI, the faster your sprinkler head, or even smoke detectors have an RTI assigned to them, the faster they go off. Most buildings, like most of your office spaces, they're going to have what's called a quick response sprinkler head, and they're going to have an RTI of 50 or less. A lot of your industrial occupancies, they're going to have standard response, SR heads, and they're going to have between 80 to 120 thereabouts for the RTI. And those are in units of meter seconds square root. I want you to look at something here. This is some data I just showed you a second ago, but it's plugged in with that trash bag data for the heat release. So initially, it's about half a kilowatt, 500 watts or so, and this is a few seconds into the fire. But the question is, if I have a standard 8-foot ceiling and the trash cans at the floor, let's say 1.5 feet off the floor, let's say the fire, your fire origin. How long would it take for the sprinkler head to initiate? And in this particular example, there's wide variability in terms of what you can assign it, but there's different ratings for temperatures on the sprinkler head. And a lot of the standard response heads are on the order of 165 degrees Fahrenheit. What that means is there's typically in industrial applications for standard response heads, it's what's called a eutectic metal. It's basically a solder of sorts. It's not necessarily tin lead, but when it hits, when that mass, that eutectic metal, when it absorbs energy so that the metal itself is 165 degrees Fahrenheit, it'll actually not have enough force to resist the pressure of the water, and that head opens up. So that's the principle behind it. So here in this particular spreadsheet, I have RTI represented, and I have the temperature rating as well. And I wanted to show you, I'm using the Alpert equations here. There's different varieties of Alpert equations, but what I'm doing is I'm using the equation where the fire is basically directly under the sprinkler head. And if you look here, you have the fire going, and it's a variable output because it grows over time, and then the fire kind of goes out on its own. But this gives you a kind of a profile in terms of when the sprinkler initiates. Now, if I was using a quick response head, 165 degree Fahrenheit, that's 74 degrees Celsius rating. In that kind of a fire, after you have flame ignition on that trash bag, it's going to take about, so this blue line, this darkish blue line, that is the sprinkler head temperature, that eutectic metal I described. Whereas this rougher line beside it, that's the gas temperature. So this bluish line, that's as soon as it crosses this dashed line, that's when you can expect initiation. And if you look at that, after flaming combustion starts, it's a good 3 minutes. It's about 3 minutes before you initiate that head. That's how long it takes. Now that's at 7 feet, 2.1 meters is 7 feet right there. What happens if you had a standard response in a factory industrial occupancy? And you had an RTI, which would be typical between 80 and 120, but you'd probably want to yield on the higher side, 120. Well, what happened there is I just jumped out to 4 minutes. So the response time of the head bears a significant impact in terms of when that head's going to go off. So you can as well as the temperature. So if I purchased like a 145 degree head instead of a 165 degree head, I would actually fuse that much faster as an example. So over in this time frame, closer to 2 minutes type thing, less than 2 minutes, more like 100 seconds. So there's the trade-off. The trade-off though is if you go to a lower temperature, you're going to accidentally trigger because it's next to a heater or a skylight or something along those lines. 165 degrees is typically what you're going to see in a factory environment. Now there's one other aspect of this I want to point out. So I'm going to go back to a quick response head, an RTI of 50, and take a look at your height. Your height plays a factor. If you have a standard 8-foot ceiling room with a trash can, you'd expect your response to be much quicker in comparison with, let's say, a 10-foot ceiling or a 12-foot ceiling. I'm going to jump this up. In this case, I'm going to go 3 meters. The reason I'm going 3 meters is 10 feet. Let's say the fire is a little bit off the ground, so let's say it's a 12-foot ceiling room. What you can see is the same exact fire. All I did was go from 2.1 meters to 3 meters in terms of that height. What I saw happen is I jumped from, in the case of the RTI of 50, which was about 2 minutes, about 3 minutes, 3 minutes for initiation. I jumped all the way up to an initiation of 10 minutes. So that's the ceiling height plays a huge factor in terms of sprinkler head initiation. And I wanted to take this further. In terms of the science that goes into parking garages, storage areas, high bays. There's a lot of science that Factory Mutual and NFPA has done pertaining to sprinkler performance as a function of height. So I'm going to take another example. Here's an example from a fire associated with a vehicle, a standard sedan. And if you look at it, this is about the same duration as the other fire, the trash bag fire we looked at. You can see you have at the bottom of this image, time from ignition is 2 minutes. It's going to go up to about 30 minutes. But your peak heat release rate, instead of being 115 kilowatts, such as in the garbage bag we just looked at, it's now 5 megawatts or 5,000 kilowatts. So a significantly hotter fire. You can see it burn here. The question is, how do you design a suppression system to work in a high bay location? This obviously is a high bay location, very high ceilings, in excess of 30 feet. What happens if you have even higher ceilings, such as in an aircraft carrier, for instance? Or not an aircraft carrier, but an aircraft hangar. So let's just go back to that spreadsheet that I pointed to earlier. Let's go, we have to go standard response in an industrial occupancy. So let's just go 80. 80 is the bottom end of a standard response head. And let's jack this up. Right now it's 5.5 feet, about 18.5 feet high from the fire. So I have a very hot fire. And basically 20-foot ceilings, thereabouts. I can make this a little higher. Let's go 6.5 meter, more correctly reflect a high bay situation with a car in it. So let's say you have actually about 20 feet from where the fire of the car is up to your sprinkler head. With this fire, if a fire was ignited from a vehicle, and this, the abscissa, the x-axis down here, that's in seconds. So if you look where the blue line crosses the dash line, it's about a minute and a half, a fairly fast response. But here's something to keep in mind that a lot of people don't realize. Experimental observations show that the diameter of a fire plume at any height was somewhere between 25 and 50% of the height of interest. In other words, the diameter of a fire plume is usually about 1/2 of its height, thereabouts. Okay, so if I'm up 10 feet, the diameter of my fire would be 5 feet, that kind of thing. The reason for that is air entrainment. Because hot air rises, it has a velocity that's different than the ambient air, and the ambient air pulls into that velocity and it creates this huge cone, and that angle is about 22 degrees over time. What that does is it cools down the hot gases. So the higher the gases go up, the cooler they are. And the principle for sprinkler head activation is when those gases hit the ceiling, they actually go out in a horizontal format, and at some point they will hit a sprinkler head. Typically, just as an example, ordinary hazard protection, OH, you have different standards of protection in NFPA 13, but OH, one head can protect no more than about 130 square feet. So if you do the square root of 130, that gives you about the dimensions, a little less than 12, 11, 11 and a half, thereabouts. And that's how far apart your heads typically could be in a square pattern. And if a fire is right in the middle of those 4 sprinkler heads, the ceiling jet's going to go out and capture one of those heads and heat it up. That's the principle on how suppression works. So let's jump up from 6.5 meters, about 21 and a half feet. Let's go something bigger. What if you had a high bay on the order of, and there's a lot of high bays out there, but let's go 20 meters. Let's go 66 feet. You can see here that car fire, if you're in a standard response head, which this is, 165 degree rating, take a look at what we just did. I'm 66 feet above that fire. Those heads will never go off. A lot of people don't intuitively think that. They don't realize that sprinkler suppression, it is required to be within a certain proximity of the fire. That's how you design it. And if your environment is, a high bay, a large high bay, and you have this huge fire, you're not going to be able to adequately protect that fire. And let's reduce this. Let's go down to 15. See where we're at there, even at 15 meters. So that'd be about 50 feet. 50 feet, 15 meters is about the same. You still will never trigger those heads with this particular RTI temperature rating. Let's go a little lower. Let's go to 12 meters. So you can see I do activate after about 4 minutes in that case at 12 meters, 13 feet. I'll activate again at about a little over about 4.5 minutes, and you go to 14. I'll activate at 14 at about 6 minutes, thereabouts. So that's a relationship. But when you jump from 14 meter high ceilings to 15 high meter ceilings, they'll never trigger. It'll never happen. So a lot of design needs to go into that in terms of thought, because let's go back. Let's say you had 13 meter. Let's just put this down as 13 meters. Sure, I'm going to trigger suppression at about 4.5 minutes. But how big is that fire at that point? It's absolutely monstrous. In fact, if I scroll down here to 4.5 minutes, go to about 300 seconds thereabouts, you can see that the size of the fire is 3.7 megawatts. 3.7 megawatts. That is such a hot fire, it produces such hot gases at its base that it's actually going to overpower those drops coming down. The drops will actually pick up on the high velocity of the smoke plume and get pushed aside. You won't ever be able to control that vehicular fire with a standard head sprinkler system. It won't work. So these are just some thoughts I wanted to throw out there. Let me just show you a couple pictures I put together here. Types of sprinklers. This would be a quick response bulb type. So one of those RTI 50 type heads. And then if you look over here, this would be a standard response head. It would be in the upright. So sometimes your heads hang down like a pendant. Sometimes they hang up. This is one of those that would hang in the upward direction. So this happens to be, this would be a standard response RTI, probably on the order of 100 thereabouts. So appreciate your time. Thanks for watching this. I hope there was some benefit in that. This is something a lot of people don't know. Even fire protection engineers, people that professionally do this, they don't understand that suppression systems are not foolproof. In fact, NFPA has data that clearly shows 80% of the time your suppression heads don't work. They don't adequately control a fire, either because there's a blockage or your hazard was greater than the suppression head, that kind of thing. Literally 80% of the time. So 20% of the time your suppression system really doesn't control a fire. Nuclear facilities, a little bit better, about 92% efficacy rate. But the point is, very few FPEs that I know how to calculate time for activation. And that's problematic sometimes when you're trying to design a fire safety strategy that meets the threat. And the codes don't talk about that at all. So you have to think a little bit after the codes. Think about what are you doing in designing these facilities for protection. Keep in mind everything in the codes deals with fire. That's the origination of the fire codes, whether it was the what year was that? 18, let's see, it would have been 25, 175 year fire. I don't know, about 1850, I guess. That's when that Boston fire rolled through. And basically, significant strides were made after that in the United States regarding NFPA protection. Anyway, thanks for your time. If you have any questions on this or other subjects, go ahead and drop a comment. We'll go ahead and make something happen. Thanks for your time and have a good day.